Hello and welcome back to California Geology. I'm Dr. Robert Lopez, and today I want to continue on with the transverse ranges and some geologic structures. So if we look over here, the other type of slip is the strike slip fault. So we talked about the dip slip. Now for strike slip, remember strike is a compass direction. So we're looking along strike here. And so in this case, it'll be kind of toward the northeast. And what will happen is the movement of the blocks will be in the strike direction. So either down this way, up that way, or in this case, in the opposite direction. And then it's really your reference point, how you face a fault. So if you're standing on this side of the fault, looking at the fault here, as you approach a fault, you'll see that if you're walking on this, let's say this is a coal seam, some sort of coal formation, and as you reach the fault, you see that it's offset. You would have to step to the left to reach that same coal seam. By the same token, if you turn yourself around and put yourself here, on this side of the fault and face fault, remember this side over here is your left side, this is your right side over here, so you'd reach the fault and you'd have to step again to the left. So no matter which way you approach the fault, you would have to step to the left in that case. So this is what we call a left lateral strike slip. Left lateral strike slip. And in Southern California, the transverse ranges, there's two prominent left lateral strike slip faults. One is the Garlock fault. The other one is the Big Pine fault. In fact, two of those I drew on my little cartoon back over here. So if we look at my cartoon, you can see that this Garlock fault would be left lateral, where this northern side is moving toward the left. And then even the Big Pine fault. The Big Pine fault is an example of a left lateral fault as well, where this unit is moving this way and this side over here is moving back that way. So again, a strike slip fault in that region there, left lateral. Now the other type of motion is the right lateral strike slip, and so in this case it's going to be the opposite sense. You'll see that as you approach the fault, the opposite side moves to the right, no matter which way you face the fault. So right lateral strike slip, and obviously the example is the San Andreas. There's also the Elsinore fault and the San Jacinto fault down in Southern California that have this sense of motion. Now there's a special type of fault in the transverse ranges called a blind thrust, and it occurs under the LA basin as well. And these blind thrust faults are unusual in that they don't necessarily reach the surface. And we'll talk more about those in a moment, these blind thrust faults. But they're related to that big bend in the San Andreas fault. And remember when I did plate tectonics, I talked about these bends and how they relate to, whether they relate to a compressional stress or a tensional stress, depending on the direction of the bend. So for example, in this case here, if this plate over, let's say this is north up here and south over here. So this would be the Pacific plate on this side here. So the Pacific plate is moving toward the north, and when there's a bend toward the left here, sometimes a left bending fault, you'll see that you'll result in compression. And compression will lead to the big bend and the uplift of mountain ranges, in this case the transverse ranges. Now we call that a restraining bend. So restraining bend squeezed up the ranges: Santa Monica Range, San Ynez Mountain, San Gabriel, Santa Susana, Topa Topa Mountains, all those in Southern California, San Gabriel, San Bernardino Mountains as well. Now, remember earlier during the Miocene time, we had a releasing bend where the bend was going towards the right. And so in this case, we resulted in tensional stresses and we made pull-apart basins. So here, again, if we're looking north over here and south over here, the Pacific plate has been moving toward the north here, northwest, and so in this case we see a tensional stress, a basin that forms here. So we can form some deep offshore basins in that region there. Now when we look at the blind thrust in more detail, there's two important features I want you to know about these blind thrusts. So obviously they're going to be a reverse fault, but the one thing is that the fault does not reach the surface. And the other thing is, at the surface, it ends in these anticlinal forms, right? Anticlinal forms. So the anticlinal fold grows over buried faults. So here's a couple of diagrams here or in the diagram showing this example. So here we're seeing a shortening here. We're squeezing, having compression, and then we see these fractures here, right? So this block is moving up relative to this block here. So the hanging wall is moving up, foot wall is moving down. But instead of these faults breaking the surface, they result in these anticlines. See these anticlines? You also get a syncline in here, but the anticline is where the blind thrust fault will be. And so if we look over here, I've kind of drawn my same little cartoon here. And so two examples of anticlines related to this type of blind thrusting. There's one called the Wheeler Ridge. And Wheeler Ridge is right near the Grapevine. If you're going on I-5, right before you start, you pass Bakersfield, and as you start going up into the Tejon Pass up there, there'll be a ridge to the west, and that ridge is Wheeler Ridge, and it's an anticlinal form. In fact, part of the California aqueduct system, the pumps are there. They have to pump water up over those over that ridge there, and then up over the Grapevine. Now, the other one that's really important is the Santa Monica Mountains. And the Santa Monica Mountains also have a blind thrust here. So here's a map I want to show. And if we zoom in a little bit on this guy here, I want you to see that there is this fault with open teeth there. Open teeth. So remember the teeth refer to a thrust fault, right? Where this plate is being pushed down and this plate's rising over the top. So this would be the upper plate and that's the lower plate. In this case, in the Santa Monica Mountains, we have one here, but it's one of the blind thrusts. So these mountains are resulting from this compressional stress due to movement along the Big Bend. So in fact, I have another map here. Let's look at this one. This might show a little, yeah, here it is. So this is showing a little bit more detail and showing the open teeth here, which indicates that blind thrust in the Santa Monica Mountains here. There are other ones, and the reason I wanted to use this map, because this map actually has it over here. And so there's this one here that's pretty important called the LCN Park Thrust. Again, see it has an open teeth. And that fault line, or that blind thrust is buried, and it goes directly under Los Angeles. And it does have a potential for a magnitude 6 or greater earthquake. So that's one of the problems facing Los Angeles, is that the LA Basin also has these blind thrust faults. And on these faults, there's been, in recent years, there's been several earthquakes. In fact, let's look down here. So we talked about the Santa Monica blind thrust, the LCN Park blind thrust under Los Angeles. And then other blind thrust faulting results in squeezing have caused 3 major earthquakes in Southern California. And so the first one, it was in 1971. That was magnitude 6.4. Caused quite a bit of damage. Freeways came down. Hospital buildings were... So in fact, after that earthquake, a law was... When I talk about earthquakes, I'll talk about this law. It's called the Alquist-Priolo Law. And the Alquist-Priolo Law basically states, the California legislature passed it in 1971, states that you cannot build within 100 feet of an active fault because of this earthquake potential. So that was one of the results from this 1971 earthquake in the LA region. Then the next one, I remember this one. I was in Southern California at the time. This Whittier Narrows earthquake, magnitude 5.9, that also occurred along a blind thrust. And then the magnitude 6.4 in Northridge in 1994, which caused $9 billion worth of damage. And so these were quite large earthquakes. And they were significant in that they occurred under a metropolitan, heavily populated region. So that's why there was so much damage. So these two are showing the 1994 Northridge earthquake here. And you can see that it's on a fault that doesn't reach the surface. And also the 1971 San Fernando earthquake and another fault that doesn't quite reach the surface. In fact, what's at the surface are these anticlinal mountains here. The Santa Susana Mountains in this case. So these are the top of the anticline, which really reflects that there is a blind thrust at depth. And this shows some of the aftershocks related to that blind thrust faulting. There's another map over here showing this compressional diagram showing the North Ridge epicenter and then the focal depth down here along this blind thrust here, and then here the Santa Susana Mountains on top. So that's indicating that earthquake there. In fact, let me show you a little cartoon here. And this is, I got this from Tanya Otwater from UC Santa Barbara, and it's going to show compression along this LA basin and the transverse ranges, and how we're going to take what was once under sea level, compress it, and move material, expose it to erosion. So we'll run this little 16 seconds. So here we start seeing compression. We start seeing those reverse faults. We start making deep basins over here. We're uplifting the mountains over here. Look at the folds forming over here. Then we'll see some erosion, and then that's what we end up today. So you can see here is the Pacific Plate, Santa Monica Mountains. Here are the Topa Mountains over here, Ojai Valley, the Santa Clara River, Oak Ridge, Thousand Oaks, Simi Valley over here, the Oxnard Plain back over here. And so also note that we have in fact, this is called the Ventura Basin. Ventura Basin, very deep, one of the deepest ones, probably over 10,000 feet of, 10 kilometers, which is about 30,000 feet of sediment, an incredibly deep sediment. The deepest one in the Transverse Ranges basin area. So anyway, that's showing those compressional forces there. So one of the things about the Transverse Ranges, it is a geologic oddity in that the ranges run east-west instead of north-south like the rest of the North American Cordillera. Remember, the Cordillera is a series of mountain ranges, valleys, plateaus, rivers that really are related in terms of their western United States. It goes all the way from Alaska down into Mexico, which involves the North American Cordillera, from the coastline to the Rocky Mountains. So it's a very large region. And so you can see here our Transverse Ranges run east-west. And so we'll look at the Transverse Ranges, and then here's the LA Basin, again, really part of this Peninsular Ranges province. And another thing about these Transverse Ranges, it's one of Earth's most rapidly rising mountain ranges. There are sedimentary rocks that are as young as 200,000 years old that formed underwater. There's marine fossils in them, and they're easy to identify because they look like modern shells, right? And now they're uplifted and folded to a 30-degree dip angle, and so during these earthquakes. And so if you think about the recent earthquakes I just talked about, the three significant ones, the San Fernando earthquake 71, that resulted in 2 meters of uplift, 6 feet of uplift in that earthquake. The Whittier Narrows was a blind thrust fault, but there was some doming of the anticline there as well. And then the 94 North Ridge earthquake resulted in 70 centimeters, so maybe about a little over 2 feet of uplift. So each of these is recording that compression and that tectonic uplift.